In this video, I will cover part 3 of the lab, which is demultiplexing samples. And I have a separate video linked in the lab instructions that explains what demultiplexing is and why it's important for high throughput sequencing. In this video, I'm just going to focus on how to do what we need to do, but please watch the other video for a little bit of background about what demultiplexing is. So what we're doing is basically going to that demultiplexing stop. We're changing the number of sequences it's going to use for QC, which is quality control, from 10,000 down to 1,000. So we go back to DNA Subway here. We click demultiplex. We want to change this from 10,000 to 1,000, and then click demux reads. And that'll give you a message with a little spinning wheel that says it is processing, and what it's going to show is information saying that your job is currently running. Results will be displayed here once they're finished. This should take about 10 to 15 minutes-ish, just as a heads up. What I'm going to do is switch to a different project where I've already done this, so I can show you what the results look like. So let me go to my projects. Okay, so this is demultiplexing. It's the same data set that we're using, but I did it over the weekend. And so when your project or your job is done running, you're going to have this window here where it has results and then your demultiplexing summary. So we'll click on that. It's going to load for us, and we want to take note of a couple different things, some of which you'll need to include in your lab report, some of which you'll need just for subsequent steps in this DNA Subway analysis. So from the Overview tab, which is the one we're on, we want to note the minimum and maximum number of demultiplex sequence counts. So that's this top table here, demultiplex sequence counts. The minimum is 2354, maximum is about 51,000. So that basically means out of all the samples we just put into our project, and DNA Subway demultiplexed them and decided which of those high throughput sequencing reads belongs to which sample. The sample with the smallest number of reads had 2354 reads. The sample with the largest number of reads had 51,217 reads. So take note of those two numbers. If we scroll down, the next table is per sample sequence counts. So again, what it's showing us similar to that overview we just looked at, but this is showing us for each of our total 18 samples, how many sequence counts were recovered for each of those samples. So remember, this is that max number we just saw. This is a particular sample that had it. This is that minimum number we noted in the table above, and this is the particular sample that has that. So we can save this whole table for future reference. You can download as a CSV file, and that'll save it for you. The other thing we want to look at is in the Interactive Quality Plot tab. So let's go back to the top here of this window, click this other Interactive Quality Plot tab. And what we're looking at here is essentially for both forward and reverse reads. So remember when we first set up our project, we said that we were doing paired end sequencing. So what that means is that for each fragment of DNA that you're sequencing it from two different directions. That's why you have this forward read and also this reverse read. It's very similar to when we talked about PCR, how you have a forward and reverse primer, and then you're amplifying the DNA region in the middle. It's a very similar concept here. So because these are paired end reads, we have two different tables, one for forward reads and one for reverse reads. And what these plots are showing us is the quality of the reads, both for forward and reverse. So if we look at these graphs, let me make this a little bit bigger. We're looking at for the forward reads right here, we have the quality score on the y-axis. I'm not going to go into the details here, but basically like 20 is the minimum quality score we would want to keep. The higher the quality, the more confident we are in our data. That's the data we want to use, is the one that we're confident in. And then the x-axis is the sequence base. So all of the reads that we're using for this project were about 240 base pairs long. And this is giving you the average for each one of those 240 bases across all of our samples, what the quality is at that particular base pair position. And in general, for all high throughput sequencing, the quality drops off at the end of the read. And so what we want to do is zoom in on that region and figure out which ones of those reads we want to throw out because they're low quality and we don't want to use them. So what you can do is use this little cursor here to click and then drag to highlight this region of the graph we want to look at in more detail. And then when you let go, it's going to zoom in. And so basically what we want to look at here is where we want to keep reads or bases here only where the bottom of this box, so these are box plots, so the bottom of the box represents the first quartile. We want to keep reads only if the bottom of that first quartile is above 20. So if we look here, these 4 positions here all have pretty low quality down up to about 15, so we don't want to use those. So what we would do is make note that 242 is basically the last base pair that has a good high quality that we want to keep. So for forward reads, I would make a note that 242 is where I want to have my cutoff for forward reads. If you double click now, it'll zoom you back out, and we can do the same thing for the reverse reads. So scroll down here and you can note that the reverse reads, the quality is a little bit lower than the forward reads, but we're still going to do the same thing and figure out where we want to cut off. So you can zoom in here like we did before. And here, like I said, you can see we're going to have to cut off more than we did before. So there's some people trim at slightly different places. I would say basically because this quality is really low, I would have this base pair. So if you look here, that's 237. I would note that 237 is the last good base pair position I want to use for my reverse reads. So make sure you make note for both forward and reverse which base pairs you want your cutoff to be. So you can zoom back out. Oh, right. And I suggest taking a picture or saving a copy of your full and zoomed in interactive quality plots. So I do that on my Mac by taking a screenshot. So if I click Command-Shift-4, a little cursor will pop up for me. I can highlight the region that I want to save, and then that'll automatically save that screenshot image I just captured onto my desktop. So I would do that for your reverse reads and your forward reads, and then also for that zoomed in picture that you took. So I would do the same thing and take a picture of that as well. Okay, if we go back to our instructions. So now if we click this back button here and then close, oh, where did my close window go? So now if you look, we now have this .2 option for us, so that's what I will cover in the next video, which will be the last step we'll do in this lab.